In this video, we're going to look at the two-second angle theorem. We will study the relation between the measure of an angle formed by two secant lines to a circle on the Euclidean plane and the measures of the arcs intercepted by those two secant lines. This theorem is also quite closely related to the two-tangent angle theorem and the tangent-secant angle theorem. In fact, it's easy to see the resemblance in the statement of these couple theorems. So now let's look at the statement of the result. If two secants intersect at a point in the exterior of a circle, the measure of the angle at the points of intersection is 1/2 the positive difference of the two intersected arcs. In the figure below, we have the angle formed by those two secant lines denoted as angle DEC, and the arcs intercepted by those two secant lines are respectively given by the arc APB and the arc CQD. So the result could be written in such a format. But on the other hand, we also observe that the arc APB is a minor arc, while the arc CQD is a major arc. So we could take away the absolute value sign by writing the result as 1/2 of the difference between the arc CQD, which is the major arc, and the measure of the arc APB, which is the minor arc. In the proof, we're going to see that the inscribed angle theorem is going to be of significant importance. So now let's look at the proof down there. The idea is to relate the angles and the arcs by introducing a triangle. So what we're going to do is going to join those 2 points, point A and point C, on the circle. Now, observing that by joining those 2 points, we form two inscribed angles of the circle, which are the angle CAD and the angle ACB respectively. And we also observe that those two angles, those two inscribed angles, are intercepting the major arc CQD and the minor arc APB respectively. So we expect these two angles are going to be of some kind of relation with our result here. And specifically, we observe that the angle AEB turns out to be another angle in the triangle AEC, along with the angle ACE. Hence, we could try to bring all these relations together and formulate the following proof. Now, the first observation is by the inscribed angle theorem, we have the measure of the angle CAD equal to 1/2 of the measure of the arc intercepted by these two chords, which is precisely the arc CQD. And for the same reason, the measure of the angle ACB is 1/2 the measure of the arc intercepted, which is APB. And the second observation we're going to use is that the angle DAC up there, it's in fact an exterior angle for the triangle ACE with the angle AEC and the angle ACE as the non-adjacent interior angles. So this observation that the angle DAC is an exterior angle of the triangle ACE leads to the following consequence, that the measure of the angle DAC is equal to the sum of the measure of the angle ACE and the measure of the angle AEC. And recall that the angle AEC, which is this angle up here, is precisely the angle CED, which we want to evaluate the measure. So we could make the following algebraic manipulation to finish up the proof. Consequently, we have the measure CED, which is precisely the measure of AEC because they are just the same angle. It would be equal to the difference between the measure of the angle DAC and the measure of the angle ACE. Well, but of course, the angle ACE is precisely the angle ACB, because B and E and C are collinear, they are on the same line. Hence, we could replace the measure of ACE by the measure of ACB up there, which in turn is equals to 1/2 the measure of the arc APB. Similarly, I'm sorry. I believe we are supposed to put CAD up there, right? But we observe that the measure of CAD could be replaced by 1/2 the measure of the major arc CQD. Hence, we could conclude that the last expression is equivalent to this expression here, which is exactly what we want to prove for our theorem. All right, so we have shown that the measure of the angle CED is equals to 1/2 the difference between the measure of CQD and the measure of the arc APB, as we have seen down there. And the proof complete.